Turn your notes to page 42. We're going to put everything together, and when we do, we call it the Standard Model. Here it is, folks. The Standard Model, that's the name we give to the most successful scientific theory humans have ever come up with. No scientific model or theory is more accurate than the Standard Model, and we give it a glorious name to match the achievement, the Standard Model. That's all sarcasm, of course. Okay, what is the Standard Model? It's a theory that uses quarks, leptons, and exchange particles to explain the four fundamental interactions and types of particles that exist. Although, we're cheating, aren't we? We can't actually explain gravity yet. We're working on that. If you solve that, you've got, 20 Nobel Prizes with your name on it. So let's take a moment and look at this picture because it's a really great summary of the Standard Model. All right, let's add some labels. Leptons, quarks, and exchange particles. We're not going to write the full word, but where are they? Well, this is just a bunch of letters. Wait, no they're not. This is up quark, charm, top, down, strange, and bottom. Here we have the electron, E negative. Here we have the electron, except heavier, that's the mu particle, or the muon. Here we have the tau particle, or the tauon. Those are all like basically electrons, right? And then the electron has its own neutrino, the mu has its own neutrino, and the tau has its own neutrino. Muon, tauon. So well, let's see, which are which? Oh yeah, these are the quarks, right? So I'll put a Q. And I do a line through my Q, just like my Z's and zeros, so it doesn't look like a 9. And these 6 down here, those 6 are the leptons. What about the exchange particles? Well, you've got your gluons, you got your photons, you got your Z bosons and your W bosons. So all of these, we're going to draw those as a squiggly line. That's how we represent exchange particles in Feynman diagrams. Okay. Ooh, Feynman diagrams, those are fun. All right, so what's next? We did this, check. First, let's jump down to here. Include a representation showing which exchange particles interact with which of these matter particles. Before we do that, these are gluons. And what do gluons, what do? They mediate the strong force, the strong nuclear force. This is a gamma symbol. Normally we use it for gamma photons, and we're just going to use it as the generic symbol for a photon at all. And photons, what do they mediate? The electromagnetic force, or the electromagnetic interaction. Z bosons and W bosons, they both mediate the weak nuclear force. By the way, why do we call these interactions the fundamental interactions of nature? Well, because forces could be like the normal force. That's not a fundamental interaction. Static or kinetic friction is a force. There's, what others? There's the applied force, F applied. There are all sorts of forces that, tension force, if you have a string that's stretched. Here's a monkey hanging from a string. Is that what monkeys look like? Should I add another one? No, now it's an insect. So tension force and the rope, or, if you have a spring, the spring force can push. Forces, that's kind of a generic term to describe these macroscopic things that we see. Interactions are way more fundamental. All forces derive from these interactions in gravity. So we're missing, that's the only one we're missing is gravity. Okay. So the strong force, gluons, act on what? Just quarks. The electromagnetic force, these photons, this force or interaction acts on anything with charge. These are all negatively charged, -1, right? They're all basically electrons, just heavier and heavier. And these all have charge, up and down quarks. So these are all affected, by the electromagnetic force. Bosons are the most comprehensive. They act on everything. So what's the Higgs boson? Because there's this other thing hanging out on the side. This particle physics theory, it really should be called field physics or wave physics, because what are particles? They're excitations in quantum fields. So every electron that has ever existed has been summoned from an electron quantum field. And positrons, or positive beta particles as they're called, the anti-electron, they also come from that same quantum field. The same thing is true for quarks, right? There is some quantum field for quarks. And so, you can get an up quark popping out of this quantum field. You can get anti-up quark or an up anti-quark. But here's the thing that was kind of weird. So like here's the machine, the standard model. And you input these particles into the standard model, and it spits out a bunch of like rules and, properties of the particles. And it says, oh, electrons have this charge and they have this spin and all these other properties. But they said the standard model, the machine didn't really work. It said that electrons have no mass. And this is just nonsensical. The model was broken. Clearly this is wrong. So Peter Higgs famously proposed maybe there's another field that we have not yet accounted for. And that field became called the Higgs Field. And he said these other particles, right, like the electron, the quarks, they interact with the Higgs field. And this is possible. The different fields, the particles, they can interact with each other, like these fields. Even these fields could interact, I believe. So these particles interact with the Higgs field. It's like walking into a crowded room. Imagine there's a party at the Large Hadron Collider at CERN, and there's all these really well accomplished physicists, and here I come, your lowly high school physics teacher, and I enter through the door, and if I want to go to the other side of the room, it's super easy, right? I make my way there as fast as possible. There is nothing slowing me down or getting in my way. But if Peter Higgs, the infamous Peter Higgs, walks into the room, everyone is going to flock to him, and he's going to talk to this person and then talk to this person, and they're all going to kind of flock around him. And so he interacts much, much more with the room, and he moves across far slower than I do. The Higgs field is like those people. Photons do not interact with the Higgs field, and so they move across at the speed of light, the fastest possible. Electrons and up quarks, and every other quark, these do interact with the Higgs field. And because they slow down, it means they do not move at the speed of light. It means they have mass. This is a strange property, but only things that are massless particles, they are unencumbered by mass. Those are the ones that travel at the speed of light. And anything with mass goes slower. If you don't believe me, watch me the next time I try to run a mile. Watch me the next time I try to run half a mile, or just like 5 steps. Mass slows you down. Slows me down, I should say. But it slows particles down too. So here's the thing. There's this field, this mysterious field. How could we ever possibly test that the field exists? I mean, quantum fields are kind of invisible to us. You can't see them. All you can see is the particles they produce. Well, guess what? If the Higgs field is actually real, then you should be able to produce a Higgs particle called the Higgs boson. And that's what they proved existed through a tremendous amount of testing and a phenomenal amount of effort. I mean, the largest machine ever to be built, the Large Hadron Collider, was created in large part to test to see if the Higgs boson existed. And the great achievement that it discovered that the Higgs was actually did exist, and it found the Higgs boson, which says, hey, if the Higgs boson exists, the field must exist too. And so yes, this Higgs mechanism, this Higgs field, is what gives these other things their mass. The electron, the anti-electron, the quarks, the mass those particles have comes from this Higgs field, this Higgs mechanism.